Inhalational anesthetic agents are typically in liquid form at room temperature and pressure. To administer them, they must first be converted into a gas or vapor. This conversion process is called vaporization, and the equipment that facilitates it is known as a vaporizer. The vaporizer ensures that the gas is mixed in the right concentration with oxygen or air, keeping the patient safely anesthetized. In this video series, we will explore the physical principles behind vaporization, the working mechanisms of vaporizers and different types of vaporizer. Let's begin with the physical principles behind vaporization. Before discussing vaporizers, we first need to understand what a vapor is. To grasp this concept, it is essential to know about something called critical temperature. When a gas is compressed intensely, the particles that make up the gas are brought closer to each other. As you continue compressing, at some point, the particles will coalesce, turning the gas into a liquid. However, if the gas is above a certain temperature known as the critical temperature, no matter how much pressure is applied, the gas will not turn into a liquid. A substance that is below its critical temperature can exist in both its liquid and gaseous forms. The gaseous form of such a substance is called a vapor. If enough pressure is applied, this vapor will condense into a liquid. In contrast, a gas that is above its critical temperature remains in its gaseous form. No matter how much it is compressed, it will not condense into a liquid. Let us take isoflurane as an example. The critical temperature of isoflurane is about 200 degrees Celsius. Therefore, at room temperature around 21 degrees Celsius and atmospheric pressure of 760 millimeters of mercury, isoflurane exists as a liquid vapor phase. Now, imagine you are on the planet Venus. The surface temperature on Venus is about 500 degrees Celsius. Since the room temperature on Venus is higher than the critical temperature of isoflurane, isoflurane will be only in gaseous form. If all of this seems confusing, remember that at room temperature on Earth, the gaseous forms of common anesthetic agents exist in liquid vapor phase. For those interested in learning more about critical temperature and pressure, please visit my video on anesthesia gas supply systems. The link is provided below. When the anesthetic agent is placed in a tight container, the vapor molecules exert pressure on the walls of the container. This is called vapor pressure. Over time, the pressure exerted by the vapor stops further liquid from vaporizing by compressing the vapor molecules back into liquid. At this point, the vapor is said to be saturated, meaning it cannot hold any more molecules and the system is in equilibrium. The pressure at this point is called saturated vapor pressure. SVP is important because it tells us how easily a substance can turn into vapor at a specific temperature. Each anesthetic agent has a unique SVP, so vaporizers need to accurately control the amount of vapor released based on the SVP of the agent at room temperature. SVP is influenced by two factors: the physical properties of the volatile agent and the surrounding temperature. As the temperature increases, more liquid molecules gain the energy to escape into the vapor phase, increasing the vapor pressure. When the saturated vapor pressure of a liquid equals the external atmospheric pressure, the liquid reaches its boiling point. At this point, all the liquid rapidly turns into gas throughout its entire volume. So if the agent has a lower boiling point, it can easily vaporize at a given temperature and atmospheric pressure, meaning that agents with lower boiling point have higher SVP. Another relationship we notice here is that atmospheric pressure has to be equal to the SVP to make the liquid agent boil. So if the atmospheric pressure is low as in high altitude, vapor pressure easily reaches the lower outside pressure, allowing the agents to boil sooner. So, we can deduce that the most volatile of the agents are those with the highest SVPs at room temperature. At any given temperature, these agents also have the lowest boiling points. You can check the table given in the earlier slide. For example, Desflurane boils at 22.9 degrees at an ambient pressure of 760 millimeters of mercury. This means it easily turns into vapor at room temperature, making it challenging to control its concentration during anesthesia. For this reason, Desflurane vaporizers have the mechanism to compensate for change in atmosphere. Modern vaporizers for most agents automatically adjust for altitude changes, ensuring safe dosing. Older vaporizers may require manual adjustments to ensure proper anesthetic delivery at higher elevations. The quantity of anesthetic vapor can be measured either by its absolute pressure in millimeters of mercury or kilopascals, or as a volume percent, which represents the amount of vapor in relation to the total gas mixture. The pressure exerted by the vapor can be explained by Dalton's law of partial pressure, which states that, in a mixture of gases, each gas exerts pressure independently of the others, and the total pressure is the sum of the partial pressures of all the individual gases. Let's say a patient is breathing a gas mixture that contains 49% oxygen and 49% nitrous oxide with 2% of an anesthetic agent like sevoflurane. With the total pressure of the gas mixture at sea level of 760 millimeters of mercury, we can calculate the partial pressures of each component as follows. So the total pressure of 760 millimeters of mercury is the sum of the partial pressures of all these gases. These concentrations are determined by gas analyzer in the anesthesia circuit and can also be ascertained from vaporizer dial. Now, why is the partial pressure important? The partial pressure of the anesthetic agent determines its physiological effect, as the agent's partial pressure drives its absorption into the bloodstream and tissues. And when we adjust the concentration on the vaporizer dial setting, we are indirectly adjusting the partial pressure of the anesthetic agent relative to the oxygen and other gases. Volume percent expresses the relative ratio or proportion of gas molecules in a mixture. The volume percent is a relative measure and doesn't change with pressure or temperature under normal conditions. For instance, if a gas mixture contains 2% sevoflurane, this means that 2% of the gas molecules in the mixture are sevoflurane molecules. As mentioned earlier, the concentration can be determined by setting on the vaporizer dial and also from the partial pressure measured using a gas analyzer. Expression of quantity of anesthetic gas in percentage is important because the vaporizer dial is set to deliver gas in proportion to oxygen, air, or nitrous oxide. Anesthesiologists often need to adjust the concentration of anesthetic gases delivered to the patient. Percentages are straightforward for setting and adjusting the concentrations on vaporizers. The minimum alveolar concentration that determines anesthetic potency is also expressed in volume percent. Expressing MAC in percent ensures that the value remains consistent regardless of changes in atmospheric pressure, making it a reliable measure under different conditions. So it makes sense that anesthetics are delivered in percent, though the action of it depends on the partial pressure. The minimum alveolar concentration is a measure of anesthetic agent potency. It is defined as the concentration that produces immobility in 50% of patients who undergo a standard surgical stimulus measured at sea level at 760 mm of mercury. Mach is expressed as volume percent of alveolar gas. Expressing Mach in percent ensures that the value remains consistent regardless of changes in atmospheric pressure. The Mach of different inhalational anesthetics are given here. A lower Mach value means that a smaller concentration of the anesthetic is needed to achieve the desired anesthetic effect. Thus, anesthetics with lower Mach values are considered more potent. At their SVP, most anesthetic agents are very potent. Let's take an example of sevoflurane, which has an SVP of approximately 160 mm of mercury at 20 degrees Celsius. Sevoflurane's Mach is about 2%, meaning it is potent enough to induce anesthesia at this low concentration in the alveoli. Now when sevoflurane is fully saturated at atmospheric pressure of 760 mm of mercury, the concentration would be around 21%. This is significantly higher than the 2% Mach value, implying that sevoflurane at its SVP is approximately 11 times more potent than the amount needed to achieve anesthesia in 50% of patients. Therefore, vapors must be diluted to provide clinically meaningful concentrations, and the way this is done is by mixing oxygen and other gases. We have repeatedly stressed that partial pressure of the anesthetic in the central nervous system is responsible for the anesthetic effect. So one should also think of Mach in terms of partial pressure and not only volume percent. Terms like minimum alveolar pressure, minimum alveolar partial pressure and partial pressure at 1 Mach are used to describe the partial pressure of an anesthetic agent at a concentration of 1 Mach. For instance, 1 Mach of isoflurane is equivalent to a PMAC1 of 8.7 mm of mercury. When administering inhalational anesthetics at different altitudes, it is crucial to consider how altitude affects the partial pressures of anesthetics. The partial pressure of inhalational anesthetics is the pressure exerted by the anesthetic gas within the mixture of gases in the lungs. It is calculated by multiplying the atmospheric pressure by the concentration of the anesthetic gas. For example, if a sevoflurane is administered at a 2% concentration, the partial pressure at sea level would be 15.2 mm of mercury. At 5,000 feet, the partial pressure would be 12.64 mm of mercury, and at 10,000 feet, the partial pressure would equal 10.46 mm of mercury. The decrease in partial pressure of inhalational anesthetics at higher altitudes means that the anesthetic potency can be affected. To maintain the same anesthetic effect, at higher altitudes, a higher concentration of the anesthetic may be required to achieve the same partial pressure and clinical effect as at sea level. However, modern vaporizers have a compensation mechanism to account for pressure changes. Vaporization is the process where molecules transition from the liquid phase to the vapor phase, and this requires energy. This energy is known as the latent heat of vaporization. It is defined as the amount of heat needed to convert a unit mass of liquid into vapor. For instance, at 20 degrees Celsius the latent heat of vaporization for isoflurane is 41 calories per gram. The heat of vaporization is inversely related to the ambient temperature, meaning that at lower temperatures, more heat is required for vaporization. During the vaporization of an anesthetic agent, the necessary heat is drawn from the remaining liquid agent and its surroundings. As vapor forms and heat energy is lost, the temperatures of both the vaporizer and the liquid agent decrease. This temperature drop causes the vapor pressure of the anesthetic to decrease. Without any compensatory mechanism, this decrease in vapor pressure would lead to a reduced output of vapor. Modern anesthetic vaporizers ensure consistent anesthetic delivery by managing temperature changes effectively. They use external heat sources like electric heaters and heat exchangers to maintain stable temperatures. High thermal conductivity materials such as aluminum and copper distribute heat efficiently. Advanced thermostatic control systems with sensors and automatic adjustments keep the liquid anesthetic at a constant temperature. We will discuss all of this when we look into the design of the vaporizer. Specific heat refers to the number of calories required to increase the temperature of 1 gram of a substance by 1 degree Celsius. In simpler terms, specific heat is a measure of how resistant a substance is to heating up. A substance with a high specific heat takes more energy to get warmer, while a substance with a low specific heat heats up quickly with less energy. For example, water has a high specific heat, which means it takes a lot of energy to raise its temperature. This is why water heats up and cools down slowly compared to many other substances. When liquid anesthetic evaporates, the latent heat of vaporization causes the remaining liquid's temperature to drop. To counter this, heat must be continuously supplied to keep the temperature stable and ensure consistent vaporization. Materials with a high specific heat such as copper require more heat to change their temperature just like water. Therefore, for the same amount of heat lost during vaporization, temperature changes in these materials are more gradual. This property is advantageous because it slows down temperature fluctuations, ensuring that the anesthetic liquid remains at an optimal temperature for vaporization. Thermal conductivity measures how well a material allows heat to flow through it. Vaporizers are designed using materials with high thermal conductivity like copper and aluminum to facilitate efficient heat transfer, quickly distributing heat throughout the vaporizer. This efficiency helps to counteract any cooling effects from the vaporization process. The purpose of a vaporizer is to add anesthetic vapor into the fresh gas flow in a way that the output of the vaporizer delivers the set concentration of the anesthetic agent accurately. Vaporizers have advanced from simple inhalers to today's sophisticated devices which are microprocessor controlled, temperature regulated, and equipped with flow sensing technology. The design improvements were driven by the introduction of potent inhalational anesthetics, the unique properties of some agents, a deeper understanding of their mechanisms, and the need to address issues in older vaporizers such as variations in output due to changes in temperature and pressure. In this video, we will briefly look into how the vaporizers are classified and mostly focus on the basic design of vaporizer. The prequel to this video on the physical principles of vaporizer will be beneficial to fully grasp the concepts in this one. Although there are various ways to classify vaporizers like the one shown here, a single vaporizer might have one or several characteristics from different classifications. Some of the classification are obsolete due to technological advances too. However, in my view, this classification allows us to understand the vaporizer design in a more systemic way. So we will look into them one by one. We will start our discussion with the methods used in vaporizer to regulate the output of the vaporizer. It includes variable bypass and measured flow. The variable bypass system consists of an inlet and outlet and the vaporizing chamber. Fresh gas enters the vaporizer through the inlet. It connects to a gas supply line, allowing a mixture of gases like oxygen or nitrous oxide to flow into the system. The vaporizing chamber is where liquid anesthetic is converted into vapor. It features a heating element to assist in vaporization and is designed to maximize contact between the liquid and gas, ensuring efficient vaporization. We shall look into them later. The outlet is where the vaporized anesthetic mixed with carrier gases exits the vaporizer. The reason it is called bypass is because the vaporizer has a bypass pathway that allows a portion of the fresh gas flow to bypass the vaporizing chamber while another portion passes through the chamber to become saturated with anesthetic vapor. And it's variable because the dial on the vaporizer controls the concentration of anesthetic gas delivered to the patient by adjusting the ratio of gas that passes through the vaporizing chamber versus the gas that bypasses it. For this reason, it is also called concentration calibrated. As we have seen, the variable bypass method splits the gas into two streams. The ratio of fresh gas flow bypassing the vaporizing chamber to the flow passing into the vaporizing chamber is referred to as the splitting ratio. Let's begin with this simple vaporizer containing sevoflurane to understand how splitting the fresh gas changes the percentage of delivered anesthetic. The saturated vapor pressure of sevoflurane is 157 mm of mercury at 20 degrees Celsius. The vapor covers the liquid sevoflurane. Now let's add a fresh gas or oxygen flow to get that anesthetic vapor. The resultant gas flow will now have the vapor of sevoflurane in it, assuming the flow is slow enough to let it equilibrate. This is 157 mm of mercury, or approximately 21% of total flow if expressed in percentage. This is way too much to use in practice. To lower its concentration, we need to split the fresh gas flow and only allow a proportion to go into the vaporizing chamber by making some gas bypass it. For instance, if we send 50% into the vaporizing chamber and 50% through the bypass channel, we can halve the resultant concentration of sevoflurane in the gas flow. This is because we only saturate half of the total gas with sevoflurane. Our resultant concentration is half the SVP, or 11%. In practice, even 11% is too much, as MAC of sevoflurane is around 2%. We can vary the amount of agent entering the chamber to change the resultant concentration of the gas flow. This is known as adjusting the splitting ratio, and the dial or knob on the top of the vaporizer does it. So if we have 10% fresh oxygen entering the vaporizing chamber, the resultant fresh gas will have 10% of the SVP in it. So for sevoflurane this would be about 2.1%, which is 1 MAC for sevoflurane. The concept of splitting ratio can be viewed through mathematical expression too. Let's calculate the splitting ratio for sevoflurane to be delivered at a concentration of 2% again. At full saturation, sevoflurane contributes about 157 mm of mercury to the total pressure of a gas mixture. So the concentration of sevoflurane in the gas mixture is 21%, where 760 mm of mercury is the total atmospheric pressure. To achieve a 2% concentration of sevoflurane, the splitting ratio can be calculated using the formula. Plugging in the values, we get the splitting ratio of 0.11. This means that approximately 11% of the fresh gas flow will pass through the vaporizing chamber to pick up sevoflurane, while the remaining 89% will bypass it. We can also convert this value into ratio by dividing 1 by 0.11, which equals 9 approximately. This means for every 1 part of fresh gas that passes through the vaporizing chamber, approximately 9 parts of fresh gas bypasses it. Note that this calculation is a simplified way of looking into splitting ratio, as there are many factors that impact the ratio. Variable bypass vaporizers are the most common type used in modern anesthesia machines due to their reliability and precision in delivering volatile anesthetics. Vaporizers using this method of delivering output are given here. We will talk about individual vaporizers in the coming videos. Another method of regulating vaporizer output is the measured flow method. A measured flow method is used in older types of anesthetic vaporizer. It involves a vaporizing chamber where an anesthetic agent is heated at temperature above its boiling point. The measured flow of oxygen is allowed to pass to the vaporizing chamber, which carries a vapor anesthetic at a very high concentration. In order to dilute this lethal concentration of anesthetic coming out of measured flow, it is combined with the gases passing from the main flow meter. So the operator has to set the flow to the vaporizer and bypass with separate flow meters. This means that respective flows have to be calculated for each agent for a given temperature and vapor output. Adjusting the vapor concentration with this method is a complex process. Let's briefly try to tackle it here. Let's create isoflurane at 1% with the total flow of 5 liters per minute. To create this mixture, the vaporizer must generate 50 liters per minute of vapor, which is 1% of 5,000. So 1% isoflurane in 5 liters per minute flow requires 50 milliliters per minute of isoflurane vapor diluted in a total volume of 4,950 milliliters fresh gas. The 4,950 milliliters per minute is the combined flow from the two flow meters. The saturated vapor pressure of isoflurane at 20 degrees Celsius is 238 millimeters of mercury, and this represents 31% of isoflurane. This 50 milliliters per minute is 31% of sevoflurane vapor. The rest 69% of this, or 111 milliliters per minute, is the measured flow of carrier gas or oxygen that must flow to the vaporizing chamber. This flow must be deducted from the total flow of 4,950 milliliters so that the main flow meter delivers 4,839 milliliters per minute. Adding the vapor flow, measured flow, and the fresh gas flow from the main flow meter gives 5 liters, which contains 50 milliliters of isoflurane representing 1% of the mixture. This calculation is quite complex, and adjusting the flow rates of 2 flow meters to precisely achieve the required anesthetic concentration is challenging at best. As a result, this method of regulating vapor output has become obsolete. The copper kettle vaporizer introduced in the early 1950s used measure flow method to regulate the vaporizer output. In the previous video, we learned about how the high concentration of anesthetic agents in the vaporizing chamber is diluted with fresh gas to output a gas mixture that is safe for clinical use. In this video, we are going to discuss the method used to improve the efficiency of vaporization in the vaporizing chamber to ensure consistent vaporization and even mixing of the anesthetic and the carrier gas. The methods used are flow over, bubble through, and injection technique. A flow-over vaporizer is designed to efficiently convert liquid anesthetic agents into vapor by utilizing the flow of a carrier gas, typically oxygen or nitrous oxide. The carrier gas is introduced into the vaporizer, flowing over the surface of the liquid anesthetic agent. As the carrier gas flows over the anesthetic, it picks up vaporized anesthetic molecules, creating a mixture that is delivered to the patient. The vaporizer incorporates wicks made of porous material that extend into the liquid anesthetic. Due to capillary action, the liquid anesthetic rises into these wicks, significantly increasing the surface area of the liquid that is exposed to the carrier gas. This enhanced surface area improves the efficiency of vaporization, allowing more molecules of the anesthetic to escape into the gas phase. The design of the vaporizer often includes baffles or spiral tracks that direct the flow of carrier gas. These structures lengthen the pathway of the gas over the liquid anesthetic, giving it more time and surface area to interact with the anesthetic and further enhancing vaporization efficiency. The Tech vaporizer uses a wick system for consistent anesthetic delivery. In contrast, the Goldman bottle flows directly over the liquid surface, which can be less efficient, especially at lower flow rates. In devices like the copper kettle vaporizer, carrier gas is allowed to bubble through the liquid anesthetic. This method, known as the bubble-through system, utilizes agitation and splashing to create smaller bubbles, thereby increasing the surface area of the gas-liquid interface. The size of the bubbles, depth of the liquid, and the velocity of the carrier gas flow all influence the vaporizer's output. The diagram on the left shows the complex design used in Tech 6 Desflurane vaporizer, which is an injection type of vaporizer. The diagram on the right is the simplified version to show how, by injecting a known amount of anesthetics or vapor into the gas stream, the desired concentration of output can be achieved. We will discuss this complex diagram when we see Desflurane vaporizer. Now let's move into another way a vaporizer is classified, that is based on their location. Essentially, there are two possible locations for a vaporizer within an anesthesia breathing circuit. The vaporizer can be inserted into the fresh gas line that supplies the anesthesia breathing system, known as out-of-circuit. Alternatively, it can be integrated directly into the breathing system itself, referred to as inside circuit. A vaporizer inside circuit is positioned within the breathing circuit itself. This means the anesthetic vaporization process occurs directly within the gas flow that goes to the patient. In this setup, such as in a copper kettle, the vaporizer is placed downstream of the fresh gas flow meter and directly in the patient's breathing circuit. The patient's respiratory efforts or mechanical ventilation drive the fresh gas through the vaporizer, where it picks up the anesthetic agent. The VIC system can provide a high concentration of anesthetic gases quickly because it is directly in the circuit. It is generally simpler and may be easier to use in some scenarios. But concentration of the anesthetic gas can vary with changes in ventilation parameters such as respiratory rate and tidal volume. It may be less precise in controlling the exact concentration of the anesthetic agent compared to vaporizer outside systems. It increases resistance to the breathing circuit too. A vaporizer outside circuit is positioned outside the breathing circuit, meaning the anesthetic vapor is mixed with the carrier gas before it enters the patient's breathing circuit. In this setup, such as the one found on modern anesthesia machines, the vaporizer is located upstream of the breathing circuit. Fresh gas flows from the anesthesia machine through the vaporizer, where it picks up the anesthetic agent, and then this mixture enters the breathing circuit that delivers it to the patient. The ventilator out of the system provides more consistent and precise control over the concentration of anesthetic gases delivered to the patient. It is less affected by changes in ventilation parameters, ensuring a more stable delivery of anesthetic concentration. Its location out of the breathing circuit significantly reduces the resistance to flow within the circuit. The only drawback is that the system can be complex and may require more initial setup and adjustments compared to VIC systems. However, the lower resistance to flow and more reliable performance of VOC systems make them the preferred choice in modern anesthesia practice. In the physical principle video on Anesthesia Vaporizer, we have seen that during vaporization, the liquid molecules absorb energy or heat to break free from the liquid phase and enter the vapor phase. As the liquid anesthetic vaporizes, it absorbs heat from its surroundings, which can cool the remaining liquid. This cooling effect can lower the vapor pressure of the anesthetic agent, affecting the amount of vapor produced. The vaporizers are built with solutions to compensate for that temperature changes to ensure consistent output of anesthetic agent regardless of fluctuation in temperature. The key mechanisms involved are altering the flow to the vaporizing chamber using bimetallic strips or ether-filled bellows and by supplying heat to the vaporizer. Bimetallic strips are composed of two different metals with distinct coefficients of thermal expansion bonded together, meaning they expand and contract at different lengths with changing temperature. This differing expansion rates of the two metals cause the strip to bend in either direction. The bending movement of the strip is used to adjust the position of a needle valve, which controls the flow of fresh gas into the vaporizing chamber versus the bypass channel. When the ambient temperature increases, the strip bends in a way that increases the flow into the bypass channel and reducing the flow to vaporizing chamber. This decreases the amount of gas that picks up anesthetic vapor. When the temperature decreases, the strip bends in the opposite direction, increasing the flow into the vaporizing chamber, compensating for the reduced vapor pressure by allowing more gas to pick up the anesthetic vapor. Bimetallic strips are specifically utilized in variable bypass vaporizers, which allow for automatic and precise control over the concentration of anesthetic delivered to patients. Some vaporizers use the expansion and contraction property of some liquid inside bellows to control the valve. Ether-filled bellows, just like bimetallic strips, work on the principle of thermal expansion of ether, a liquid with a high coefficient of thermal expansion. The bellows expand or contract in response to temperature changes. As the temperature rises, the ether inside the bellows expands, causing the bellows to expand as well. This expansion mechanically alters the flow of fresh gas via the valve into the vaporizer. When the bellows expands during higher temperature, it closes off some fresh gas passing into the vaporizing chamber, thereby reducing the vapor uptake by the carrier gas. When the bellow contracts at lower temperatures, it opens up more pathways to the vaporizing chamber so as to allow more anesthetic vapor to be picked up by increased flow. The other method of thermal compensation is by supplying heat to the vaporizer. The Omeda Tech 6 vaporizer is specifically designed for Desflurane, an anesthetic agent with a high vapor pressure that is highly sensitive to temperature fluctuations. The Tech 6 vaporizer is equipped with an electric heater that maintains the Desflurane at a constant temperature of 39 degrees Celsius. Desflurane has a boiling point of 22.8 degrees Celsius at standard atmospheric pressure, meaning it will boil at room temperature, cooling the Desflurane remaining due to latent heat of vaporization. This will lead to inconsistent vapor pressure. Heating Desflurane to 39 degrees Celsius in the Tech 6 vaporizer ensures that it is in a stable vapor form, making management of vapor pressure precise. The vaporizer has an internal thermostat to monitor and regulate the temperature. If the temperature drops below 39 degrees Celsius, the heater is activated to warm the Desflurane, ensuring that it remains in a liquid state and produces a consistent vapor pressure. Vaporizers can also be classified based on whether it can be used for multiple anesthetic agent or for just one single agent. Older vaporizers like Goldman vaporizers was multi-agent. Modern vaporizers like Tech series are specifically customized based on individual agents' chemical properties like saturated vapor pressure, boiling point, and minimum alveolar concentration. So they are agent-specific. Depending on the resistance the vaporizer offers, there are generally two types of vaporizers, plenum and draw-over. Plenum vaporizers have a much higher internal resistance, requiring fresh gas at above atmospheric pressure. The plenum vaporizer is driven by positive pressure from the flow meter and is usually mounted on the machine. The performance of the vaporizer does not change regardless of whether the patient is breathing spontaneously or is mechanically ventilated. The internal resistance of the vaporizer is usually high, but because the supply pressure is constant, the vaporizer can be accurately calibrated to deliver a precise concentration of volatile anesthetic vapor over a wide range of fresh gas flows. The plenum vaporizers are a variable bypass type and positioned out of the patient's breathing circuit. Tech vaporizers are plenum type. In draw-over systems, the carrier gas is drawn with negative pressure through the vaporizer either by the patient's own respiratory efforts or by a self-inflating bag with a one-way valve placed downstream from the vaporizer. Its performance depends on the minute volume of the patient and therefore must have a low resistance to gas flow. The design of the draw-over vaporizer is much simpler. In general, it is a simple reservoir mounted in the breathing attachment. Draw-over vaporizers may be used with any liquid volatile agent, including older agents such as diethyl ether or chloroform. Although it would be dangerous to use Desflurane. Because the performance of the vaporizer is so variable, accurate calibration is impossible. Examples include Oxford Miniature Vaporizer and Epstein-McIntosh Oxford Inhaler.